Good morning. In this section, we study the fundamental discrete structure on which all other discrete structures are built, namely the set. Sets are used to group objects together. Often, but not always, the objects in a set have similar properties. For instance, all the students who are currently enrolled in your school make up a set. Likewise, all the students currently taking a course in discrete structures at any school make up a set. In addition, those students enrolled in your school who are taking a course in discrete mathematics form a set that can be obtained by taking the elements common to the first two collections. The language of sets is a means to study such collections in an organized fashion. We now provide the definition of a set. This definition is an intuitive definition, which is not part of any formal theory on sets. Definition 1. A set is an ordered collection of objects called elements or members of a set. A set is said to contain its elements. We write A is an element of A to denote that A is an element of the set A. The notation A is not an element of A denotes that A is not an element of the set A. Example 1. Describe the vowels of the English alphabet by employing the language of sets. Solution. The set V of all vowels in the English alphabet can be written V is equal to the set A, E, I, O, and U. Note that we use capital letters that are italicized to represent the set entire, and notice that the set is enclosed between curly braces and elements of the set are separated by commas. Example 2. Describe the collection of odd positive integers whose values are smaller than 10 by employing the language of sets. Solution. Let O be the set of odd positive integers less than 10. O is equal to the elements 1, 3, 5, 7, and 9. Example 3. Although sets are usually used to group elements with common properties, there's nothing to prevent a set from having seemingly unrelated elements. For instance, A2 Fred, New Jersey is a set containing 4 elements, A2 Fred and New Jersey. Remark. Sets contain unique elements. For example, the set of vowels in the English language is seldom expressed as AA, double E, double I, double O, double U. An element should only appear once. Example 4. Describe the collection of integers whose values are between 1 and 99 by employing an ellipsis and set notation. Set I is equal to set 1, 2, 3, 99. Set builder notation. We characterize all those elements in a set by stating the property or properties that they must have to be members. So in the left-hand column, we have the set builder notation, and in the right column, we have an explanation. O is the set X, where X is odd positive integer less than 10. O is equal to 1, 3, 5, 7, and 9. O is equal to X, where X is an element of the positive integers, where the script Z with the superscript plus represents the set of positive integers, and X is odd and X is less than 10. O is the set of positive integers given that X is odd and that X is less than 10. Q plus is the set of all positive rational numbers, is equal to the set X where X is an element of the reals, and X is equal to P divided by Q, where P and Q are both positive integers. Common sets include N, the set of natural numbers that includes 0, Z, that includes the set of integers, Z plus, that is the set of all positive integers, Q, where this is the set of rational numbers, and R is the set of real numbers. Example 5. The set that includes N, Z, Q, and R is the set containing the 4 elements, each of which is a set. The four elements of the set are n, the set of natural numbers, z, the set of integers, q, the set of rational numbers, and r, the set of real numbers. Remark. Note that the concept of a data type or type in computer science is built upon the concept of set. In particular, data type or type is the name of a set, together with a set of operations that can be performed on objects of that set. For example, Boolean is the name of the set, including 0 and 1, together with the operators on one or more elements of the set, such as and, or, and not. Definition 2. Two sets are equal if and only if they have the same elements. That is, A and B are sets. Then A and B are equal if and only if, for all x, x is an element of A implies x is an element of B. We write A equal B if A and B are equal sets. Example 6. The sets 1, 3, 5, and 3, 5, 1 are equal because they have the same elements. Recall that a set is a collection of unordered elements from definition 1. Note that the order in which the elements of a set are listed does not matter. Note also that it does not matter if the set is listed more than once. If an element in the set is listed more than once, 1, 333, quadruple 4 is the same as 135 because they have the same elements. Venn diagrams. Sets can be represented graphically using Venn diagrams named after the English mathematician John Venn. In Venn diagrams, the universal set U, which contains all the objects under consideration, is represented by a rectangle. Inside the rectangle, circles or other geometric figures are sued to represent sets. Sometimes points are used to represent a particular element of the set. Venn diagrams are often used to indicate the relationship between sets. Example 7. Draw a Venn diagram that represents V, the set of vowels of the English alphabet. Solution. We have the rectangle U representing all the letters of the English alphabet, and inside of U we have a circle, and inside that circle we have the vowels A, E, I, O, U. Definition 3. A set is said to be a subset of B if and only if every element of A is also an element of B. We use the notation A is a subset of B to indicate that A is a subset of B. Example 8.1. The set of all positive integers less than 10 is a subset of all positive integers less than 10. The set of rational numbers is a subset of the set of real numbers. The set of all computer science majors at your school is a subset of all students at your school and the set of all people. China is a subset of the set of all people in China. That is, it is a subset of itself. Example 8.3. Example 9.1. The set of integers with squares less than 100 is not a subset of the set of non-negative integers because -1 is in the former set, as -1 squared is less than 100, but not in the latter set. Example 9.2. The set of people who have taken discrete structures at your school is not a subset of all the computer science majors at your schools if there is at least one student who has taken discrete structures who is not a computer science major. Theorem 1. For every set I, the empty set is a subset of S, and S is a subset of S. Definition 4.1. Set A is a proper subset of B when A is a subset of B and there's at least one element in B not in A. We use the notation A is a subset of B when A is a proper subset of B. Example 9.2. Consider the two sets A equal 1, 2, 3, 4, 5 and B equal 1, 2, 3, 4. B is a proper subset of A and we write B is a proper subset of A. because the element 5 is not in element B and is in element A. The size of a set. Definition 4. Let S be a set. There are exactly n distinct elements in an S where n is a non-negative integer. We say that S is a finite set and that n is the cardinality of S. The cardinality of S is denoted by 2 vertical bars around S, or the cardinality of S. Example A, 10. Let A be the set of odd positive integers less than 10. A is equal to 1, 3, 5, 7, and 9, and the cardinality of A is 5. Example 11. Let S be the set of letters in the English alphabet. Then the cardinality of S is 26. Example 12. Because all null sets have no elements, it follows that the cardinality of the null set is 0. Definition 5. A set is said to be infinite if it is not finite. Example 13. The set of positive integers is infinite. Definition 6. Given a set S, the power set of S is the set of all subsets of the set S. The power set of S is denoted P of S. Example 14. What is the power set of 0, 1, 2? P of the set 0, 1, 2 is the empty set, the set containing 0, the set containing 1, the set containing 2, the set containing 0, 1, the set containing 0, 2, the set containing 1, 2, and the set containing 0, 1, 2. Example 15. What is the power set of the empty set? What is the power set of the set containing the empty set? Consequently, the power set of the set containing the empty set is the set containing the empty set. Remark: if a set has n elements, then its power set has 2 to the n elements. Cartesian product. Definition 7. The ordered n-tuple A1, A2 through AN is the ordered collection that has A1 as its first element, A2 as its second element, and AN as its nth element. Definition 8. Let A and B be sets. The Cartesian product, and let's just italicize that and make that red. The Cartesian product of A and B is denoted A cross B and is a set of all ordered pairs AB where A is an element of A and B is an element of B. Hence A cross B is an element of the form A comma B where A is an element of A and B is an element of B. Example 16. Let A represent the set of all students at a university, and let B represent the set of all courses offered at a university. What is the Cartesian product A cross B? Solution. The Cartesian product of A cross B consists of all ordered pairs of the form A comma B, where A is a student and B is a course offered at the university. The set A cross B can be used to represent all possible enrollments of students in courses at a university. Example 17. What is the Cartesian product of A, where A is the set 1, 2, and B is the set ABC? The Cartesian product of A cross B is 1, A, 1, B, 1, C, 2, A, 2, B, and 2, C. Example 18. Show that the Cartesian product B cross A is not equal to the Cartesian product of A cross B, where A and B are as in example 17. The Cartesian product of B cross A is A, 1, A, 2, B, 1, B, 2, C, 1, and C, 2. This is not equal to A cross B as shown below, which is 1, A, 1, B, 1, C, 2, A, 2, B, and 2, C. Definition 9. The Cartesian product of the sets A1 through AN is denoted A1 cross A2 cross AN is a set of ordered n-tuples A1 through N where A sub I belongs to set A sub I for I equal 1 to n. In other words, A1 cross A2 cross an is equal to the set, including